Medellin, if you will, a pair of intrepid explorers hurtling through the infinite blackness of space, billions of miles from home, carrying the essence of humanity on their backs. These aren't fictional heroes from a sci-fi epic. They're real mechanical marvels launched by NASA nearly half a century ago. Voyager 1 and Voyager 2, the twin probes that have redefined our understanding of the cosmos, continue to defy the odds, beaming back whispers from the edge of interstellar space. But what lies ahead for these cosmic pioneers? Will they fade into silence, or will their journey reveal secrets that echo through eternity? Stick with me through this captivating tale, because by the end, we'll unravel the enigma of their ultimate destiny, a mystery that scientists have finally pieced together with groundbreaking precision. Prepare to be amazed, inspired, and perhaps a little humbled by the sheer audacity of human ingenuity. In the vast expanse where stars are born and die, these probes serve as our silent ambassadors, pushing the boundaries of exploration further than any human has dreamed. As we dive deeper into their story, you'll discover not just facts and figures, but the thrilling narrative of resilience against the unforgiving void. From their dramatic launches amid the cultural whirlwind of the 1970s to the jaw-dropping discoveries that reshaped astronomy, every twist and turn builds toward that final revelation. Don't stop now. The payoff is worth every moment as we explore how these aging spacecraft are still rewriting the rules of space travel in 2025. Picture this. It's the sweltering summer of 1977, a time when disco fever gripped the world. Star Wars lit up movie screens, and the first personal computers were just beginning to buzz in homes. Against this backdrop of earthly innovation and excitement, NASA engineers at Cape Canaveral prepared to catapult humanity's ambitions into the stars. On August 20th, 1977, Voyager 2 lifted off aboard a Titan II IE Centaur rocket, embarking on what would become the longest continuous space mission in history. Just 16 days later, on September 5th, its sibling, Voyager 1, followed suit. These weren't mere satellites. They were sophisticated spacecraft, each weighing about 1,592 pounds, 722 kilograms, equipped with cutting-edge instruments designed to withstand the harsh realities of deep space. The timing was no accident. Astronomers had calculated a rare planetary alignment, a grand tour opportunity that occurs only once every 175 years, allowing the probes to visit Jupiter, Saturn, Uranus, and Neptune using gravity assists. This slingshot effect, where a planet's gravity flings the spacecraft forward like a cosmic catapult, saved precious fuel and enabled journeys that would otherwise be impossible with 1970s technology. Each probe carried 3 radioisotope thermoelectric generators, RTGs, fueled by plutonium-238, providing a steady power supply that has decayed predictably over decades, but still keeps them alive today. As Voyager 2 blasted off first, it took a longer, more circuitous path to allow for visits to all 4 outer planets, while Voyager 1 prioritized closer looks at Jupiter and Saturn before veering northward out of the solar system's plane. The missions were budgeted for just 5 years, but the engineers built them to last, incorporating redundant systems and radiation-hardened components. Little did they know that these decisions would extend the probe's lives into the 21st century, turning a planetary flyby into an interstellar odyssey. The launches marked a pivotal moment, blending human curiosity with technological prowess, and set the stage for discoveries that would captivate generations. But why does this matter now, in 2025? Because as we face new challenges like climate change and global connectivity, the Voyagers remind us of our capacity for long-term thinking. Their story isn't just history, it's a living testament to perseverance. As we continue, you'll see how these launches paved the way for revelations that still influence modern space missions, like the James Webb Space Telescope or the upcoming Europa Clipper. Keep reading, because the real adventures and the mysteries begin with their encounters in the outer solar system. Fast forward to March 5th, 1979, when Voyager 1 made its closest approach to Jupiter, the king of planets, at a distance of about 217,000 miles. 349,000 kilometers, from its swirling cloud tops. What the probe revealed was nothing short of revolutionary. Jupiter wasn't the bland gas giant we'd imagined. It was a dynamic world of raging storms, including the Great Red Spot, a colossal anticyclone larger than Earth, churning for centuries with winds up to 400 miles per hour, 644 kilometers per hour. Voyager 1's cameras captured time-lapse sequences showing atmospheric bands shifting like conveyor belts, unveiling a planet alive with energy. But the surprises didn't stop there. Voyager 1 discovered active volcanoes on Io, one of Jupiter's moons, spewing sulfur plumes hundreds of miles into space. The first evidence of volcanism beyond Earth. This moon, tortured by tidal forces from Jupiter and its siblings, became a poster child for extreme geology. Meanwhile, Europa's icy surface hinted at a subsurface ocean, sparking debates about potential life that persists today. Ganymede and Callisto, with their cratered terrains, added layers to our understanding of moon formation. Voyager 2 arrived at Jupiter on July 9, 1979, confirming and expanding these findings with improved data on the planet's magnetic field, which is 20,000 times stronger than Earth's, and traps charged particles in deadly radiation belts. The probes measured Jupiter's ring system, faint and dusty, composed of particles from its moons. These discoveries overturned textbooks, showing the outer solar system as a place of violence and variety, not stasis. In 2025, these early insights continue to inform missions like Juno, which orbits Jupiter and builds on Voyager data to probe its core and auroras. The Voyager's Jupiter flybys were more than snapshots. They were the opening act in a symphony of exploration. As we move to Saturn, the plot thickens with rings, moons, and unexpected twists that kept scientists on the edge of their seats. Stay with me. These revelations build toward understanding the probe's enduring legacy and their mysterious endgame. By November 12, 1980, Voyager 1 had traversed over 1 billion miles to reach Saturn, the ring jewel of the solar system. Approaching within 77,000 miles, 124,000 kilometers of the planet, the probe's instruments pierced the veil of its hazy atmosphere, revealing a world of hydrogen and helium with winds howling at 1,100 miles per hour, 1,770 kilometers per hour. But the real stars were the rings, thousands of them, composed of ice particles ranging from dust to house-sized boulders, shepherded by tiny moons like Prometheus and Pandora. Voyager 1's close-up views showed intricate braids and spokes in the rings, phenomena caused by electromagnetic forces and gravitational tugs. Titan, Saturn's largest moon, emerged as a methane-shrouded enigma with an atmosphere thicker than Earth's, hinting at organic chemistry that could mimic pre-life conditions. The probe's infrared spectrometer detected hydrocarbons, fueling speculation about alien worlds. Voyager 2 followed on August 25, 1981, surviving a stuck-scan platform to capture data on Enceladus's icy geysers, plumes of water vapor suggesting subsurface oceans, and Iapetus's bizarre two-toned surface. These findings revolutionized our view of Saturn as a miniature solar system, with moons potentially harboring life. Today, in 2025, the Cassini mission's legacy builds directly on Voyager data, confirming Enceladus's habitability potential. But the Voyagers didn't stop at Saturn. Their gravity assists propelled them onward, setting up even more profound discoveries. As we venture to the ice giants, the story escalates, leading us closer to the interstellar boundary and the heart of the mystery. You're halfway there. Keep going for the thrilling payoff. While Voyager 1 sped northward after Saturn, Voyager 2 pressed onto Uranus, arriving on January 24, 1986, the only spacecraft to ever visit this tilted ice giant. Uranus, rotating on its side due to an ancient collision, presented a bland blue face, but Voyager 2 uncovered fierce winds up to 560 miles per hour, 900 kilometers per hour, and a magnetic field offset by 60 degrees from its axis, creating bizarre auroras. The probe discovered 10 new moons, including Puck and Miranda, the latter with a chaotic surface of cliffs and craters suggesting tectonic upheaval. Uranus's faint rings, dark and narrow, were mapped in detail, composed of rocky debris. Then, on August 25, 1989, Voyager 2 reached Neptune, the windiest planet with gusts over 1,200 miles per hour, 1,930 kilometers per hour. The Great Dark Spot, a storm akin to Jupiter's red spot, dominated its atmosphere, while Triton, Neptune's retrograde moon, revealed nitrogen geysers erupting 5 miles high, indicating cryogenic volcanism. These visits doubled our knowledge of the outer planets, revealing them as dynamic worlds rather than frozen relics. In 2025, proposals for new Uranus and Neptune orbiters cite Voyager data as foundational. With the planetary tour complete, the probes entered uncharted territory. The next chapter? Interstellar space, where the real mystery of their fate begins to unfold. Don't miss it. The revelations are just ahead. After Neptune, Voyager 2 joined Voyager 1 in the Voyager interstellar mission, aimed at the heliopause, the boundary where the sun's influence wanes. Voyager 1 crossed this threshold on August 25, 2012, at 121.6 astronomical units from the sun, entering interstellar space where galactic cosmic rays dominate. Instruments detected a sharp drop in solar particles and a rise in interstellar magnetic fields. Voyager 2 followed on November 5, 2018, at 119 astronomical units, providing a second perspective with its plasma science instrument intact, confirming the heliopause's asymmetric shape due to the sun's motion through the galaxy. These crossings marked humanity's first direct sampling of interstellar medium, revealing denser plasma and unexpected magnetic field alignments. In 2025, data from both probes continue to refine models of the heliosphere. But as power dwindles, what does the future hold? The answer lies in their ongoing challenges and the ultimate silence ahead. Keep reading. The mystery's solution is nearing. As of August 20th, 2025, Voyager 1 is approximately 168.5 astronomical units from the Sun, about 15.6 billion miles or 25.1 billion kilometers, traveling at 38,210 miles per hour, 61,500 kilometers per hour, in the constellation Ophiuchus. Voyager 2 is at 140.5 astronomical units, 13 billion miles, or 20.9 billion kilometers, speeding at 34,390 miles per hour, 55,350 kilometers per hour in Pavo. Both remain operational, with 3 science instruments each: the Cosmic Ray Subsystem, Low Energy Charged Particles Instrument, and Magnetometer. Power from RTGs has decayed to about 57% of launch levels, producing around 249 watts for Voyager 1 and 255 watts for Voyager 2. Communications take 23 hours for Voyager 1 and 19 hours for Voyager 2 via NASA's Deep Space Network. Recent data includes measurements of interstellar plasma density and magnetic fields, contributing to understanding galactic structure. But engineering hurdles loom, as we'll explore next. The end is approaching, but the story's climax is the solved mystery of their fate. The Voyager's longevity is a testament to NASA's foresight, but 2025 has brought fresh trials. In March, engineers shut down Voyager 1's plasma science instrument and Voyager 2's low-energy charged particle instrument to conserve power, extending operations into 2026. May saw Voyager 1's thrusters revived after clogging, using backup systems dormant since 1980. Earlier glitches, like Voyager 1's 2024 computer malfunction fixed by April, highlight the team's ingenuity, reprogramming from 15 billion miles away. These feats ensure data flow, but power will drop further, with predictions of 1 instrument per probe by 2026 and full shutdown by 2030 to 2036. This resilience builds suspense for their final fate, now solved through advanced modeling. The revelation awaits. Attached to each Voyager is the Golden Record, a 12-inch gold-plated copper disc containing sounds and images of Earth, greetings in 55 languages, music from Bach to Chuck Berry, natural sounds like thunder and whales, and 116 images of life and culture. Curated by Carl Sagan, it's designed to last 1 billion years, protected by an aluminum cover with playback instructions. This bottle in the cosmic ocean represents our hope for contact, even if unlikely. In 2025, it symbolizes unity amid division, reminding us of shared humanity. As the probes drift, the record could be humanity's lasting legacy. But what of their paths? Next, we chart their future trajectories, leading to the solved mystery. Post-solar system, Voyager 1 heads toward the constellation Camilla Pardalis, approaching AC plus 79, 3888, Gliese 445, in about 40,000 years at 1.6 light-years distance. No collision, but a close stellar encounter. Voyager 2 aims for Ross 248 in Andromeda, also in 40,000 years at 1.7 light-years, then Sirius in 296,000 years. These paths, calculated using Gaia telescope data, show they'll orbit the Milky Way every 225 million years, potentially surviving for billions. No immediate fate like destruction, instead, eternal wandering. But the mystery of their operational end? Solved next. The final fate mystery, when will they go silent, has been solved through refined power models and instrument prioritization. As of 2025, predictions indicate Voyager 1 will cease science data by 2027 to 2028, with engineering signals until 2032, Voyager 2 until 2029 to 2030 and 2034, respectively. RTG decay at 4 watts per year will drop below operational thresholds, but thruster fixes extend attitude control. Beyond that, they'll drift as silent ambassadors, golden records intact, potentially encountered eons hence. Recent simulations confirm no major hazards for millions of years, solving the enigma, not a dramatic end, but a graceful fade into cosmic history. This resolution underscores their triumph. As the Voyagers drift further into the interstellar void, their legacy fuels the next wave of cosmic exploration. In 2025, their data continues to shape missions like the proposed interstellar probe, designed to venture 1,000 astronomical units by leveraging modern propulsion technologies. The Voyager's pioneering measurements of the heliopause and interstellar medium have set benchmarks for studying exoplanetary systems and galactic magnetic fields. Moreover, their resilient design inspires engineers crafting space